Well, this is your virtual Big Bean, Dave Harris. And before we kick off our series of virtual coffee cabinets with live members, I thought I'd play one we recorded back in 2020 during the pandemic. So you get sort of a flavor of what it's like, and also a very good presentation by one of our own members. So without further ado, let's take a look at that video.
Bob, go ahead and let's move on to the program. You got it.
Okay. I've introduced Brad Parkinson many, many times before, and I was trying to think of something that you might not know about him. And so this is going to be an extremely brief introduction, Brad. The only thing I could come up with is that Air Force Colonel Brad Parkinson received his commission at the U.S. Naval Academy. So it's a pleasure to introduce Brad. He is, I believe, still the Edward C. Wells Professor of Aeronautics and Astronautics, the W. Hansen Experimental Physics Lab. He's co-principal at investigator there at Stanford University. He's known as the father of the GPS. And he's going to talk to us about the third rock from the sun, or he called it the third planet, parameters of the third planet. So it's a pleasure to have you with us, Brad Parkinson.
Thanks, Bob. This particular little talk is a tribute to the lack of oxygen on our hikes, you see, because we were hiking along and I was thinking about things, and I said, gee, it might be interesting to put together a little talk about the third rock. And so I said, Bob, maybe I could do this. And he said, sure, that's a good idea. Of course, I hadn't put the talk together, and one thing led to another. But at any rate, that's what I'm going to do. First of all, I'm going to try to share my screen. And there we go. Is everyone seeing this? Can you see it?
Yes.
Yes.
Okay, let me get.
It sounds like Tara hasn't been working out. She'd be more firmer.
Thanks, guys. I know this is going to be fun. So I have titled this in a way, Why Tara Isn't Firma. Some observations on what I call our instability. You can interpret that any way you wish. Can you see my pointer moving around there?
Yeah.
Okay. So I really like this particular view of the Earth because it's done to scale. And what it shows, of course, is that the place that we all reside in is this thin little scab, this little crust on the top of an enormously hot, molten, by and large, molten ball of, I think it's predominantly iron and nickel. And somewhere in the middle, there's a solid core because of the enormous pressures. It's still very, very hot, but there's a solid core. And there are, of course, some things that people call atmosphere. And that also is a very, very thin topping to our whole Earth. And as a consequence, that governs some of the things that happen. And let me see if I can get this to advance. So the other point I wanted to make from this, I've been in the satellite business more or less for the last 40, 50 years. The Earth satellites that most of us talk about, I couldn't get the spelling right, having been at that long, but satellites is spelled wrong, of course. But the point that's being made here is the satellites, by and large, just skim around the Earth. The typical altitude is 150 to 600 nautical miles for those that are close in, including the space station. It becomes a very congested place, of course, but it has one big advantage, and that is the slight atmosphere up there tends to bring drag and energy out of those orbits and bring those satellites down fairly quickly compared to the high altitude, such as GPS, which is It couldn't even be shown on the scale we have here because it's 3.5 Earth radii above the Earth. So the point I'm going to be talking to is Terra isn't permanent. I have a series of subtopics. You'll have to forgive me because when I put together one of these topics, I tend to go wherever I find something interesting. So if you expect total coherence here, you have been talking or you are listening to the wrong person. So I'm going to try to be interesting. But meanwhile, here's what I'd like to talk about. Third planet, motions and shape is what I'm calling it. First, I'm going to talk a little bit about what I call the jitters, stress relief. And I'm going to talk about the wobbles, which actually has a formal name for those of us that have been in gyroscopes and that sort of thing. It's called nutation. And then drifting, the fact that our North Pole star is temporary, and how that might have influence on what we do. It turns out this also has a name from gyroscopic theory. It's called precession. And then I'm going to talk a little bit about moving and spinning. We're on a merry-go-round, of course, but there's much more than that. And then I'm going to talk a little bit about the center and the shape of things, which way is down, and the difference between gravitation and gravity, which presumably you haven't thought a lot about, but if you, by the time you get done, you'll be ready for the quiz. So jitters. Jitters in this particular talk, it refers to the fact that the crust, that thin crust, is wiggling a lot. And we say a lot. Most of these motions tend to be about at the rate that fingernails grow. So what we have is a large Pacific plate, which is shown here, the rim of fire around it. I could show the whole world, but this is the most interesting to those of us who live in California. And the thin crust is being pushed by the magma forces beneath the crust. And there's two seams, if you will. There's a pull-apart seam, which is which tends to be, let me mute that. There's a pull-apart seam, which tends to be out in the oceans. And then there's a convergent seam, which tends to be collisions and usually along land somewhere. And everyone's familiar with the fact that those collisions occur all around the rim of fire, and as a matter of fact, are partially responsible. And of course, most of us living in California know that the problem is not the motion, it's the lack of motion. It's when these plates get hung up. If you go over to Parkfield, they have continuous earthquakes, but they're not very big. And that reflects the fact that the plates that are involved at Parkfield don't get hung up. And as a result of not getting hung up, they have a series of small motions, little earthquakes, but presumably they have building codes to account for that. But the problem that occurs, of course, in the case of the jitters is when the stress is relieved, it releases enormous energy, and we call that an earthquake. And the issue that is frequently, or the goal that is frequently sought is, can we predict earthquakes? And now, of course, you're going to get back to one of my favorite subjects if you did not expect that. Let me advance this. Okay. So back in 1974, we thought we could use GPS to survey to a meter. And the surprise is we discovered we could do it to a millimeter, about 1/8 of an inch kind of thing. As a matter of fact, we could do it in 3 dimensions. And the result of that is that we're able to measure the cleavage and the collisions that occurs along the fault. Now, some of you may recognize, here's Seattle, and this whole area is an extremely unstable area for earthquakes. And they're going to have a big one of these days. I mean, big, on the order of 8. Because the Juan de Fuca plate is pushing in to the North American plate. And what made GPS unique was not simply the accuracy and what you see here. By the way, these little red lines, there's a calibration. 4 millimeters. So that's a velocity of 4 millimeters per year. So what it is showing here is the various stations that are along here and which way they are moving. But the point is, GPS does it in 3 dimensions. And the geodesists love that. When we had the Loma Prieta quake, I was at Stanford and I had the 2 very best GPS receivers at Stanford, and the geodesists didn't. So one of the professors, as soon as that quake broke apart, one of them came over to my office and said, "Can I borrow your geodetic class receivers?" And I said, "Yes, you may." And he took them up, put them on either side of the fault line, and they had that enormous break that was sometimes called the World Series earthquake. Some of you, I happened to be in the Mountain View area when that happened. And what he discovered using the 2 receivers that I gave him was after the break occurred, there was a subsequent slow motion that continued for almost 2 weeks. And they had never been able to observe that before, and in particular, observe it in 3 dimensions. So the point is, it tells us how to characterize the earthquakes, but what about predicting them? Well, there's some hope that we can certainly do better. And this is an area in Canada, and I'm going to blow this chart up, but let me say something about this at the beginning. This is motion on either side or across a boundary or fault line in which there are plates moving. And this is a plot over a period of about 4 or 5 years. And what you can see is that the motion builds up and then there's an abrupt release. Perhaps not a very large earthquake, but certainly an event. And if my arrow will stay on, you can see that this event occurs with great regularity. And when I say great, you can see the differences in the period from 426 days to 424 days, and typically 448 days. So the point is, if you were near this, and this was an event that you were curious about or had some probability of harming the population, you would have a basis for saying when you get this far deviated from the green mean line of motion, that you're going to have an earthquake pretty soon. And in this case, perhaps predicting it to a few weeks would be possible. And I'd like to show you that in just a little bit bigger view. Now, the interesting thing to me is the precision with which we're measuring this. 1 inch on this scale is from there to here. So what you're seeing is not large, violent motion, but it's very regular, and it tells you the precision with which we're measuring it. So the question is, does that give you hope of predicting earthquakes? Well, not with great precision. If you've ever been in the testing business for samples of strength of metals, for example, in my early engineering days, we would do that in a mechanical engineering lab. And predicting exactly when something is going to break apart, you can't do it. You come pretty close, but you can't do it. So I don't think there's much hope of doing a very precise prediction of earthquakes, but there certainly is some hope of understanding when the probability of having an earthquake has gone up. And of course, that's a useful piece of information. So I would call this almost predictable. And these are, in this vernacular, what I would call the small jitters. So I don't know if you picked up on it. When I showed this chart in the beginning, there was a little red dot here. And that little red dot is Yellowstone National Park. So the next part of the jitters story is a lot more than jitters, actually. This is a picture of the park, and that yellow boundary is something that the scientists call a super volcano or a very large caldera. And the point is, this is an area, the whole area, that is, but has a great potential for exploding. And on their super volcano scale, this is 8 out of 8 on the volcanic explosivity index. It has erupted 3 times over the past 2 million years or so. And if you run the calculation, you divide that by 3, you say, okay, every more or less 700,000 years, it's going to blow up. And most recently, it did it 640,000 years ago. So maybe in the next 10 or 20,000 years, we should start to worry about this. The statement the European Science Foundation has made, it is the greatest catastrophe since the dawn of civilization. But of course, there haven't been people around in the last 640,000 years, or at least 640,000 years ago. So presumably it's not a big deal. This is a little better picture of that volcano. This is in 3 dimensions, and you can see these are miles along the side. So it's kind of a deep area underneath there in which the magma is flowing around and disturbing the crust. And for comparison, Mount St. Helens was 1 to 2 cubic kilometers of stuff that was thrown out. Yellowstone would be 240 to 2,500 cubic kilometers of stuff. So the point is, this is sort of an interesting area. And again, I'm not going to spend a lot of time talking about GPS today, but GPS is being used to measure various points that exist on the surface and reflect the underlying magma and what its instability really is. And again, you can see 2 centimeters per year. So the scale is, that's about an inch, and that's about an inch. And the blue is the vertical motion, and the red is the horizontal motion. So you can see now kind of a confused picture. And if you go on a little bit in time, you can see this picture. So in the first picture, the magma is starting to expand, and this is in the period of 06 to 09. But fortunately, in 10 to 11, the magma has subsided again, which reduces any cause for alarm. So this is what I would call a super jitter, and I don't know if you would even use the term jitter for this particular situation. The GPS monitoring of that 3 dimensions is, of course, a key. So let's turn to the second subject, and that is drifting. The fact that Polaris, our guide star, our North Star, is temporary. This is a picture of the Earth, which is, of course, spinning in the direction that you see it here. And somewhere there is a spin axis defined by that rotation, and that's called our North Pole, of course. And it's propitious that it points to a particular star. There is no star, of course. There is no such star in the southern hemisphere, but we have a North Star right now. Now, because the Earth is slightly bulged, it acts like a gyroscope. And a gyroscope, when torqued, moves perpendicular to that torque. I'm not going to get into the details of that. I'd be glad to discuss it. But the point is, the moon and the sun both exert a torque on the Earth, and that's a torque, sort of a twisting motion. And because of that twisting motion, the spin axis of the Earth slowly describes a great big circle. And it stays tilting the 23 degrees off the ecliptic plane, that is to say, the plane of the Earth's orbit around the sun. And it does this fairly slowly. It takes about 26,000 years to do this complete rotation. And you, as the man in the street, say, well, that's kind of interesting, but I don't think it really is going to affect me today. It probably won't. But there is a longer term thing that's kind of interesting. So this is a plot in the sky. Here we are at 2000, and here is, everyone remembers the Big Dipper and the fact that the North Star is sitting here in the end of the handle. And as time goes on, looking up, it's going to rotate around like that, okay? And at some point, it'll be over here. I think this is Cygnus, the swan. Somebody may be able to correct me on that. But at any rate, 4,000, 6,000, 10,000 years from now, this motion, which we call precession, is going to cause us to rotate around to this position and, of course, continue in a closed circle. Well, so what? Does that really affect anything? Is perhaps a question that's legitimate. Well, it turns out it does. And it turns out it does it for sort of an interesting interaction, because the Earth itself, here's the sun, and here is the Earth going around it. And it turns out we're looking up, so it's going around like this. It turns out we're looking down. So it turns out as the Earth goes around, because the orbit is eccentric, it is closer to the sun here, and hence it's warmer, not a great deal, but somewhat during this period than it is in this period. And it turns out, because of the way the Earth is tilted, again, because of that precession, we are closer when we are tilted away, which is the northern hemisphere's winter. Does that make sense? I hope it does. So that means in the northern hemisphere winters, with the current period, you're warmer to the sun, which somewhat compensates for the normal winter coolness. And as a result, in the northern hemisphere, you would expect it to be a little warmer in winter than a picture over a period of 25,000 years might dictate. On the other hand, if you go to the other side, you'll see that summer in the north and winter in the southern hemisphere is further away. And I think that may have some influence on why, if you've ever noticed the temperatures, Antarctica is a lot cooler than the North Pole in the wintertime even. But over time, that's going to change. And that tilt is going to change. And as a result, it will, in about 10,000 years, hang on to your hat here, in about 10,000 years, it will be cooler in the northern hemisphere in winter. The impact of that, of course, we'll just have to wait and see. I don't think I'll be around, but I think Bob Mott will still be with us. Now, let me turn to another subject, and that is the wobbles. And the Earth axis moves in a funny little path. So if you could stand on the North Pole, or maybe you could actually stand on the South Pole, that pole actually wiggles, and it has a period of about 430 days. And this is a description of the motion. Now, it isn't very large. It's about 10 meters. But if you're trying to maintain the accuracy of GPS, it turns out it's important, because that would add to your confusion on what latitude line you were on, because the generally accepted way that you measure latitude is 90 degrees is the North Pole. So that 90-degree fiducial, if you will, is wiggling around with this motion. Now, for most of us, including even me, that's a pretty esoteric thing, except just to point out that in terms of the wobbles and our unstable Earth, that GPS has to account for it. Now let me turn to moving and spinning. Of course, everyone knows we're moving about, the whole Earth is spinning. This is a picture of a globe, of course, and we're at some latitude here, and the Earth is carrying us around, and it does that in 23 hours, 56 minutes, and 4 seconds. Here we're talking about our rotation relative to the stars. If you were talking the sun, of course, it's very close to actually 24 hours, but the correct calculation is done relative to the stars. And we're rotating with that period. And it turns out at the equator, the circumference is about 40,000 kilometers. So we can divide this number by that number and get an average equatorial speed of 465 meters per second. But we're not at the equator, and we have to adjust for that by taking the latitude of SLO, which happens to be 35 point something degrees. And when we multiply that out, we discover that we're going at 381 meters per second. Now, of course, we don't perceive that because the air mass is doing the same thing. But it turns out it actually does produce a centripetal force, or actually a centrifugal force. It tends to push us out, much as a merry-go-round would do. And we have to compensate for that in terms of our measurements of what we see as gravity. But meanwhile, I'll note that at sea level, this calculation would be that we are actually moving a little over Mach 1, or about 0.4 of a kilometer per second. And of course, at our latitude, we do that more or less continuously, slight modulation if we're driving in a car, but nothing worth getting excited about. But actually, our velocity is much more complex than that. Terra firma is really trucking. I just showed you why we would say that we're moving 0.4 of a kilometer per second, about a quarter mile per second, because of the rim speed of the Earth. But the Earth, of course, is going around the sun, and it's doing that at about 19 miles a second. And it's even much more complex than that because the whole solar system is out on the periphery of the galaxy. Thank God, because otherwise there'd be a lot of other stars around. But it's out near the edge of the galaxy, and it is moving around the galaxy at 135 miles a second. But then even greater complication, the galaxy center is moving towards something called the Great Attractor. And we're moving in that direction at 620 miles per second. So the motion that we actually have is the vector sum of all three of these. Not of great interest to you, but I thought it was sort of curious. And the Great Attractor itself, they don't know much about it, but it has a mass that's 100 quadrillion times greater than our sun. And its size extends 500 million light years. And it's made of both visible matter and then this dark matter that no one has seen and no one has proved really exists. But I think the generally accepted physics theories now say that there is something called dark matter. Well, the last area is the center of the Earth and the shape of things, which way is down. I have exaggerated the Earth's bulge here. And of course, the gravitational attraction, for many point out here, is directly to the Earth. But what we feel like, what is measured by a plumb bob, has to adjust for the Earth's spin. And we would quantify this as 32.16 feet per second squared as the gravitational attraction equivalent. This is about 2/10. So it's a significant but not substantial development. Of course, if the Earth was spinning fast enough, we would just spin right off. And as a matter of fact, if the Earth was spinning such that the period was 84 minutes, you would actually be an Earth satellite. And your rotation rate would exactly compensate for gravity. And that's, in a certain sense, the reason that the satellite stays up, is that the centrifugal force going out is exactly compensated by gravity coming in. And the result is you just slowly float around. So Except for the equator and the North Pole, everywhere else, a plumb bob does not point to the center of the Earth. And it turns out if you're a navigator, and there are some other reasons that you might get excited about that. But it's worse. There are many local anomalies in the direction and magnitude of local gravity. And these reflect the fact that there are deep trenches, right here. And there are high mountains, like right here. And they all change both the magnitude and the direction. If you're trying to navigate by measuring a star angle, the height of a star above the horizon, you must account for this if you're trying to really get good precision. So I've come to the end of what I want to talk about. So we, sitting on our little third rock from the sun, we are jittering, we're wobbling, we're spinning, we're moving at high velocity, and we don't know which way is down. What could possibly go wrong? Thank you.
Okay, you'll have to unmute if you want to talk.
Yeah, I'd be glad to answer any questions people might have.
Great presentation, Brad.
Thank you.
Fascinating. I've often wondered how fast we were really moving through space.
I have to be honest, because I knew that we were doing all that, but I had not quantified it. And it wasn't until I got into this talk that I discovered those astounding speeds, which are significant percentages of the speed of light. That last one is.
I saw a program on Yellowstone and the incredible damage it would do to the United States especially would be, and they were showing how far east and north it would affect, and depends on how big the reaction would be in the volcanic explosion. We hope it doesn't happen in our day, that's for certain, or any time to any of our ones that are left on this earth after us.
Actually,
Brad,
that's a good
can you hear
point.
me?
Let me just say that given the uncertainty and how long that period is, we are actually into the region where history has shown it is possible that the whole thing could blow. Now, go ahead, Bob. I'm sorry.
Yeah, that's right. I had always been taught that the universe is expanding, and yet you're talking about the great attractor. It sounds like the universe is contracting. I'm confused.
Initially, they thought that expansion was slowing down. And since then, with more careful observations, they now think that it's speeding up. See, the idea would be there was a big bang and the whole thing blew apart.
Yeah.
But hopefully it would get all sucked back together again. But most of the observations, I think, today are showing that it is moving away faster. And as a result, there are some people who have a theory of multiverses, multiple universes, that there's another out there somewhere that we can't see. Frankly, the whole thing blows your mind. And if you've ever sat on your back in a canoe in the middle of a lake where there's no background light and you're just looking at those stars and you start to contemplate it, it can be eerie. It is very eerie, in my opinion.
Okay.
I've got a question, Brad. You say it's pretty much not possible to accurately predict an earthquake, but how about acting to a onset of a high impact earthquake? Does GPS or any other system provide an anticipation there of when it will get to where I'm at versus when an earthquake started somewhere close by or far off?
Actually, the alarm system that exists, for example, in Japan, we're supposed to have one. I'm not certain how well it works. Japan, the whole country is instrumented with 600 to 800 high precision GPS receivers, and they have an alarm network. The speed of propagation of that shock wave through the crust of the earth is pretty well understood. And you have a matter of not seconds, but certainly, well, it depends on how far away you are, of course. But if you're a reasonable distance away, first of all, the earthquake shock is falling off as 1 over r squared. But the second thing that's happening is that you do have some delay, and you may have time in a 10 or 15 second or 30-second period to take shelter, get underneath something so that the building you're in doesn't fall on you. In terms of actually predicting the big ones, that the San Andreas is the example that we always here in California worry about. And it is unzippering. Yeah, some people call it zippering and unzippering. It's unzippering in sections. So it'll rip in a given section, but not in other sections. So it'll stress relieve here and then not stress relieve other places. They can have general predictions, but I don't think they have any great, by general predictions, I mean the next year or two, what the probability is of having a big one. They can do that. But in terms of taking shelter or any other action, I mean, it's like the COVID, it's coming. And predicting whether you're going to be the person who gets it, it's hard.
I have a comment, I guess, rather than a question. You referred to centripetal and centrifugal force. I have heard physicists refer to centrifugal force as the engineer's headache cure, because their world doesn't exist.
No, it does not. It's a direct consequence of the kinematic equations of motion. And I certainly could have been more sophisticated, but it is worthwhile to think of it as a force. There is a principle in mechanical engineering called D'Alembert's principle, in which you reverse the forces and attribute to them as accelerations. And I'm certain you don't want to get into that, but you're absolutely right, and I understand the criticism.
I got a comment. I have a pendulum clock, and at the back, one of the local earthquakes, my clock picked up or lost 5 minutes in about a week. And then we had the earthquake. Is there some gravity effects caused by earthquakes?
Not at the level of uncertainty in the length of your clock. The standard clock has a radium, a period that's proportional to square root of its length divided by gravity. So it turns out, unless that length changes, the variation in gravity is pretty minimal. And however, temperature variations for many clocks can cause some variation in their period and hence keeping time. I have 2 grandfather clocks that are both over 150 years old, and they keep amazing time. I mean by amazing time, better than a minute a day, a lot better than a minute a day, probably 10 seconds a day. So the point is, if you keep them reasonably temperature stabilized and you adjust the little height of the pendulum, which adjusts their period, they should do pretty well. And I don't know why your clock jumped 5 minutes.
Okay.